Um, all right, welcome everyone to today's CTMP seminar. I'm delighted to have with us Ragnar Stroberg from the University of Notre Dame. Ragnar, a little bit about Ragnar. He did his undergrad in University of California in Berkeley, followed by a PhD at Michigan State University, which he completed in 2014. And so rather interestingly, Ragnar did his PhD as an experimentalist, right? And then he went on to switch over to being a theorist. He did his postdoc at Triumph, and went on to be a visiting professor at Reed College. Right? He told me an interesting story of teaching the electrodynamics course over there in front of David Griffiths from the and yeah, then he went on to hold a research position at the University of Washington in Seattle, which is where we met, and then did a brief stint at Argonne. And now he's at the University of Notre Dame as faculty. So yeah, Ragnar does low energy nuclear theory. You guys are not used to seeing this, but I've taken it upon myself to invite people who do this to see that actually there is some theory that happens in the low energy nuclear side. Okay. Yeah, anyway, thank you very much for coming, Ragnar. Please take it away.
Okay, well, thank you, Mwande, for the invitation. I actually really like this kind of structure that you guys have suggested of two separate talks, one with the introductory and one with the more research intensive stuff. I think it's a cool way to do it. So this one is this talk is going to be all introductory material, and actually I'm not going to talk a whole lot about ab initio nuclear theory in this one. I'm going to spend most of it, basically all of it, talking about the the background, the cool things that you can do with it, try to motivate why you would want to do it, and then with the next talk, try to give you more details about how you actually go about doing it. So here it's largely not the nitty-gritty details of doing nuclear theory calculations. Let's see if I can actually advance. There we go. Okay, but first I should at least tell you what I mean by when I'm talking about ab initio nuclear theory. And really, I'm thinking of treating nuclei as a non-relativistic quantum mechanical many-body problem. And these are bound states. We're going to solve the many-body Schrodinger equation. And the kind of classic definition of ab initio that we've inherited from quantum chemistry is that they define it as an exact solution to an exact problem, which once you start thinking about it is completely crazy, because how can you ever do anything exact with more than two particles? You can't get a closed form solution for the three-body problem. So we don't want to do that, because that's not going to happen. So, and again, more realistic way of describing this, maybe not as concise, is that we want to have a systematically controlled scheme that converges to the exact solution of a systematically controlled approximation scheme that converges to the exact problem. So we're approximating the solution. We're also approximating the Hamiltonian that we're starting with in the first place. So it's a bit more of a mouthful, but I think it's more accurate. So the special important thing here is that we know we're not doing the exact thing, but we should know what it is that we're leaving out. Maybe we can't include it exactly, but we can estimate it. And then that means it should come with some error bars. We should get some theory error bars. And it's systematically controlled, so we can do a calculation, and then in principle, we can do a better calculation. The error bars should get smaller. We should be more accurate, so you can do a series of calculations, and you get more and more precise, depending on how much pain you're willing to tolerate or how big your computer is. But this is in kind of distinction to the standard low energy nuclear theory where you do a model that you can solve exactly, but you just don't have control about what you're leaving out. So then the rest of the talk is going to be kind of describing a couple of cases where that might be an interesting thing to do, because it's hard. It's a lot harder than solving a simple model. Okay, so here, what are some questions that ab initio nuclear theory can help answer? And there are many more, but these are just kind of three that I'm going to pick out. The first one is, what are the properties of matter at extreme density? So I'm talking here about the highest densities you can make. We're going to be basically nuclear matter. Then there's various questions about neutrinos, including what the nature of neutrino mass is. And then, so nuclear physics can play an important role there. And ever so briefly, I'll talk about basically the matter, antimatter asymmetry, and why is there something rather than nothing, and how we can maybe use nuclear physics to address that. Okay, so first, just some background, because this is supposed to be at the kind of fourth year undergraduate level, and maybe wanted to give some kind of a reminder of the nomenclature, the words we use when we're talking about the standard model, kind of this is the starting point for all of this. Even if in low energy nuclear physics, we're not working directly with quarks, we know that we've got to inherit all of the physics that's here. So just as a review, the standard model is basically made up of fermions, spin half fermions, and gauge bosons, and then the Higgs. So the fermions are then divided into quarks and leptons, and there are up-type quarks and down-type quarks, and then three kind of families or generations of those. So there's up, down, charm, strange, top, bottom. And then the leptons are then divided into the charged leptons, which are electron, muon, and tau. And then each of those has a corresponding neutrino. The gluon is the gauge boson that mediates the strong interaction between quarks. The photon, hopefully everyone knows, and that mediates the electromagnetic interactions. And W and Z mediate weak interactions. The Higgs gives that things mass, among other things. And we often can, sketch using Feynman diagrams, interactions between these different constituents. So for example, if we can have a charmed quark turning into a strange quark, emitting a W boson, and then that W boson might turn into a positron and a electron neutrino, for example. So that's kind of how you can interpret those pictures. And beyond that, there's also some nomenclature that may or may not come up in this talk or the next. I know that a lot of times when I'm teaching, even at the graduate level, students get confused about these if they haven't seen them before. So a hadron is just anything that's made out of quarks. A baryon is meant, so that's a balanced state of three quarks. So that could be like a proton or a neutron or any other thing that involves three quarks. And then a meson would be a quark anti-quark pair, so something like a pion or something like this. So those are going to be bosons. Okay, so that's just a whirlwind review of some of the words that we use in the standard model, because they may come up occasionally. So there we go. Okay, so on to the first question that I want to discuss. So what are the properties of matter when you go to extreme density? So we think about just matter made up of atoms, and now we just start squeezing it, and we squeeze it and keep on pushing it, and then we want to see what happens when we keep on going. So eventually we have these electron clouds around our nuclei, and these electron clouds start overlapping, and they get kind of squeezed. And you may remember from your intro quantum mechanics, electrons don't like to be squeezed. We have the Pauli exclusion principle. They don't want to be in the same place at the same time. And kind of a simple picture for this is you put them in a box. They each fill one available level, and so you keep on filling up to the Fermi level. And so that Fermi energy, the Fermi level, it depends on the density of particles there. So they, in a simple non-interacting Fermi gas, so that's just fermions in a box. The Fermi level goes like density to the 2/3 power. So as you increase the density, the energy of the last particle that you added. So in this case, the last electron keeps on increasing its density to the 2/3 power. And because energy is mass, at some point, the mass of the proton and the mass of the electron plus this Fermi energy from squeezing will get larger than the mass of the neutron. The mass of the neutron the neutron is heavier than the mass of the proton, but eventually it becomes energetically favorable for the proton and the electron to combine into a neutron and a neutrino. And you can kind of back of the envelope estimate if when you need that Fermi level to be, and then you plug it in here, and that's something like 1 billion electrons per cubic nanometer. Just to kind of give a typical point of reference, ordinary matter has something like 10 or maybe 100 electrons per cubic nanometer. A cubic nanometer is about the size of an atom. So this is, already a couple hundred, 1 million, 10 million or 100 million times the density of normal matter when this will start happening. Okay, and then you can keep on squeezing even further these nuclei because you started turning protons into neutrons. They're going to get more and more neutron rich, and you can keep on squeezing them and squeezing them and squeezing them, and eventually these nuclei are not point-like. You actually resolve the fact that they have a finite extent, and now the nuclei are going to start touching. Another way you can think about this is that the density just as a function of, say, one coordinate, and as they're spread out, I'm thinking about all the matter is in these little nuclei, and so you have little kind of lumps of matter, and as you squeeze them together, they start overlapping, and eventually it just becomes uniform nuclear matter. And maybe to make a point of reference here, if you look at nuclei as this phenomenon of saturation that happens, so what's being plotted on the left here is the charge density of various nuclei as a function of the radial distance, so distance from this origin. And so basically you keep on adding particles, and rather than the density increasing, just the size increases. So these things look like that you're just adding particles outside, keeping the density constant, so the volume increases. As you go out and farther and farther and farther, look at lead-208, and it looks like constant density until you get to the surface, then it drops off. So this system over here, this uniform nuclear matter, that it's going to be very difficult to make that in the lab because you have to squeeze things down to absurd densities. But the properties of here are basically the same as the properties of what's going on here inside lead-208. So we can use what we know about finite nuclei and then try to infer what's going on in this infinite system. And we actually can do a little bit of that, or you can get pretty far from stuff that you would see in an undergraduate level nuclear physics class. Because nuclei basically behave as a liquid drop, the volume of a nucleus scales with the number of particles because you just have a constant density, which means that the radius goes like then the number of particles A to the 1/3 power. And you can actually cook up a liquid drop formula or a semi-empirical mass formula or Bethe-Weizsäcker formula. It goes by a lot of different names, but there's only all of them have basically the same terms. So you have basically the energy, the binding energy, is just proportional to the number of particles. So we call this a volume term. But then there's a correction because some of the particles are near the surface, and so they don't feel the same binding that particles in the bulk do. And so you have a correction for a surface term, which goes like r², which then means A to the 2/3. We have a correction for Coulomb because now these are charged particles. So protons don't like being in the same place because they repel. There's an asymmetry term, which basically means that you want to have roughly an equal number of protons and neutrons. And you can understand that by the fact that each of them has their own sort of Fermi level. And if you have all protons or all neutrons, then the Fermi level becomes much higher. And so if you have an equal number, then it minimizes the energy of just because all of the available levels would be occupied. That's kind of a hand-wavy way of understanding that. And finally, there's a pairing term. Basically, you get more binding when there's an even number of protons or an even number of neutrons because they like to pair off, essentially into Cooper pairs. So with those 5 terms, basically 5 parameters, 1, 2, 3, 4, 5, you can describe the binding energies of nuclei remarkably well. But we're interested in nuclear matter. So there we want to take the limit of an infinite number of particles. So then if we just divide everything by A, we talk about the binding energy per particle. All of these other terms, if you divide by A and then take the A goes to infinity limit, go away, and you're left with just this volume term, which if you fit it to nuclear data is about 16 MeV. So we can think now about what is the equation of states of nuclear matter. So basically the energy as a function of density, you can take a derivative and turn it into pressure as a function of density. It's the equation of states. And so that's what's being plotted here. If there's no density, the energy is going to be 0 because there's no interaction going on. And we know that nuclei are going to be basically finding the minimum of that energy. So it should go down, and then there should be some negative energy, about 16 MeV per nucleon, which should be the minimum in the energy per particle. Otherwise, nuclei would be different. So we have information about this saturation point because that's what nuclei are. It turns out to be about 0.16 nucleons per cubic femtometer or so. And it's maybe not too terrible to try to interpolate between 0 and saturation density. And then as you go on, it becomes less clear what happens at higher densities. But we know because this is a minimum, it should go up. And physically, you can think about this as here's a kind of a cartoon of the interaction between 2 nucleons. There's some at very large distances, it goes to 0, and then at intermediate distances, it's attractive, and then you get to very short distances and you get repulsion, which you can think about that as these nucleons, protons and neutrons are made of quarks, and if you get them too close together, they start overlapping, and now you have the exclusion principle for the quarks, so they don't want to be in the same place at the same time, and so they don't like that, and that gives you repulsion. And so we know that the energy is going to go up. We just don't know precisely how it goes up, because most of our information comes from down here. Okay, if we keep on squeezing, something else might happen eventually. So now, say we've turned most of our protons and electrons into neutrons. So the same story can happen for the neutrons. We'll have some Fermi energy because they're again fermions, and we start stacking up, and we still have our Fermi gas. The densities are quite different. The mass is quite different. But then there's also the fact that these are you can't neglect the fact that these particles are interacting at these densities. So there's going to be some potential energy that kind of shifts the whole thing. And what can eventually happen is you can have some sort of a process like this where if you look fine details, you can have an up quark turning into a strange quark. And then it'll beta decay. So you can have what was originally a neutron turning into a baryon that has a strange particle in it. We call this a hyperon. And so now this hyperon is distinguishable from a neutron, and so it doesn't have to come in at the Fermi energy. It can come down at its own lowest energy state. So you get rid of the cost of the Fermi energy. So kind of do the inequality here. You have the mass of the neutron and its Fermi energy, and some interaction has to be big enough to make the positron, the hyperon, and then whatever potential the hyperon feels, and then this will happen. So the mass difference there is not so terrible, a couple, maybe 200 MeV. But then there's still a considerable unknown because we have these non-negligible potentials here. So this maybe could happen, but it's not as clear exactly when what density that will happen. So if we keep on squeezing even more, eventually this will become a black hole. We have a Schwarzschild radius given by this. And so so these densities we're not going to make in the lab. The only way to really make these densities is to in some sort of astrophysical object where you have gravitational forces acting on everything to compress it. This is the only place this happens. So if we think about something like say twice the mass of the sun as something that would be big enough to have these densities, the Schwarzschild radius is going to be something like 6 kilometers. And so you think about the density that corresponds to. Now we're talking about 3 neutrons per cubic femtometer. This is really high. So this is like, I would say 17 times nuclear density. So that's much higher than nuclear density, but it's not crazy higher than nuclear density. So basically, if you think about the densest matter we can make in the universe, it's not too much denser than a nucleus. And if we actually go ahead and find a place where this will happen, what we're really looking at is a neutron star, which is going to be the densest thing that is not a black hole that we can observe in the universe. And these tend to be about 1 to 2 solar masses. If they get heavier, then they tend to collapse into a black hole. And they have a radii of about 10 kilometers, so bigger than the Schwarzschild radius, so they don't collapse. And if you plug in those numbers, this now, we're something on the order of, say, twice nuclear density. So we aren't so far away from nuclei, so we can kind of hope to try to extrapolate and learn something about these and say something intelligent about them. There's a couple of caveats here. So neutron stars, as the name would imply, are going to be mostly neutrons for the reasons I described previously. Nuclei, which we have data on, are basically symmetric. They have equal numbers of protons and neutrons. So we need to have some way of using theory to go from what we do know, which is nuclei, to pure neutron matter that's showing up in these neutron stars. And this ends up being kind of non-trivial. So this is an example. This is, okay, now 12 years old. But if you want to calculate the equation of state of neutron matter, so this is basically the energy as a function of density. And all these curves are theoretical calculations with Skirm mean field calculations. And so each line is a different Skirm functional. And you can see that right around here, 1 or just below nuclear density, they all agree because they all are tuned to reproduce nuclei. But once you get out to where things become interesting, you have absolutely no predictive power. You can get any answer you want, which tells you that just fitting to nuclei doesn't actually constrain this. And so what we need to do is go about this and do an ab initio calculation so that we have some control when we want to extrapolate a little bit further out there. Okay, so that's what I want to say about that, just motivating that which I will talk about next week, how we can actually try to do that with ab initio calculations. So the next thing I want to talk about is neutrinos, and specifically the nature of neutrino mass. So we know that neutrinos have mass, or at least 2 of the 3 do. And basically we know this because if you look at neutrinos coming from the sun, they're produced in, among other things, reactions like this, where boron-8 turns into beryllium-8, and it produces a neutrino and an electron. The electron gets stuck in the sun, but the neutrino just passes right through and comes to us. And people can do solar models and know what to expect, how many neutrinos we should expect to see coming from the sun. And when people then were able to detect neutrinos, there were not as many neutrinos as expected. So this was the solar neutrino problem, which was confusing for a while. But basically the solution is that neutrinos have mass and they oscillate. So the way to understand this is that the essential point is flavor eigenstates for neutrinos are not mass eigenstates. So an electron neutrino is a linear combination of 3 neutrinos with different masses. Or you can say that a neutrino with a given mass is a linear combination of the 3 flavors of neutrino. The same thing happens with quarks, actually. So quarks are not simultaneously mass and weak eigenstates. Okay, So then if we just write down Schrodinger time evolution here, so that some neutrino, basically we've expanded this into mass eigenstates, and these mass eigenstates then propagate with e to the minus it, where the energy depends on the momentum and the mass is very small, but it's going to be different for the three different flavors. And so what essentially happens is you get oscillations which are slightly different for the three different mass components. So as you get towards the Earth, they kind of separate out a little bit in their phases. And so then at the Earth, if you now take the expectation value here, the probability or the amplitude to find a muon neutrino when you originally had an electron neutrino is given by this overlap of these. Basically, you decompose it into the different mass components, and they all oscillate. And because by the time you get to the Earth, you have a different mixture of the three different mass states, then it's going to give you some non-zero component that is not electron. So basically, there's a non-zero chance of finding a muon neutrino at the Earth, even though you started with an electron neutrino. And so that's why people weren't seeing as many electron neutrinos as they thought they would, because they turned into muon and tau neutrinos. And so based on that and some reactor experiments and looking at atmospheric neutrinos, people have worked out that because you're sensitive to the difference in mass squared between different neutrinos. So they've worked out that the difference between, say, mass 2 and mass 1 is small, and that there's a difference between mass 3 and mass 2 is also small, slightly bigger, but because we only know differences, and really you only know the magnitude of the differences, there's an ambiguity where it could be what's called a normal hierarchy, where there are 2 light neutrinos and then 1 heavier neutrino, or it could be what's called the inverted hierarchy, where there's 1 light neutrino and then 2 heavier neutrinos. And so what I'm trying to show here with these colors is the breakdown of, say, the mass 1, the lowest mass eigenstate in terms of electron, mu, and tau flavors. And since this is only sensitive to mass differences, we don't have any information on the absolute mass scale of the neutrinos. So we know that they have mass, but there's also now a question about the nature of this mass. And there are kind of 2 ways that this mass could come about. One, it could be a Dirac mass, or it could be a Majorana mass. Dirac mass is the kind of more usual way that all the other fermions in the standard model have mass. Kind of a cartoonish way of thinking about this is we have a 4-component state. So you could have a right-handed particle or a left-handed particle. And here, I think because we have spin 1/2, you can think about spin up or spin down. Or you can project that onto the direction of momentum, so it can be right-handed or left-handed. And then you can have an antiparticle that could be right-handed or left-handed. So there are basically 4 different components that you need to describe these fermions. For a Majorana particle, you just have a left-handed particle and, say, a right-handed antiparticle. And then the other 2 don't exist. Which is another way of saying this would be that the particle is its own antiparticle. By flipping the spin, you change a particle into an antiparticle. So why would we even think that this is a possibility so the weak interaction, which is the only interaction that neutrinos participate in, only couples to left-handed particles and right-handed antiparticles. So if these particles over here do exist, they're essentially sterile, they're non-interacting. So it's possible that maybe they don't even exist. So kind of another way of thinking about this is you think about, so here we have a spin and momentum. So this is more what I had in mind when I'm talking about handedness, but here this is specifically, it's called helicity, where you take the dot product of spin and the momentum. In this case, they're pointing in opposite directions, and so this would be helicity -1. Now you can imagine Lorentz boosting. So you just go to a different frame so that the momentum direction changes. Now spin and momentum are pointing in the same direction. So now you turned a left helicity particle into a right helicity particle. And this can happen if you have something with a direct mass. Or maybe that's now it becomes its antiparticle. But in any case, being able to do this, being able to boost to change the momentum requires that you have mass. So the fact that neutrinos have mass means you can think about this question. Of course, you can't change the electric charge or any other kind of charge, but just through a Lorentz boost. So to turn a particle into an antiparticle just by doing a boost, the particle shouldn't have any charges. So an electron can't do this, obviously, but neutrinos are neutral, and so it's still conceivable that they have Majorana mass rather than a Dirac mass. Another kind of cartoonish way of thinking about how the mass works for a Dirac particle, for all the other fermions, we get mass from coupling to the Higgs, and the Higgs field is just non-zero everywhere. It permeates all space. There's a vacuum expectation value. And so if you just scatter off of the Higgs over and over, because it's everywhere, you can think about diffusing along, bouncing along, or maybe even think about moving through molasses or something like this. And so particles will move more slowly, and they acquire a mass from doing that. And that's the Dirac mass picture for a Majorana mass. You can do this, but now you turn a left-handed particle into a right-handed particle by coupling to something. We don't need to really specify it just yet, but it should turn that particle into an antiparticle. So we want to know, okay, how do we actually go about testing this? How would that show up? And to do that, the answer is through beta decay. So first, just a reminder of what beta decay does. Beta decay is where we take a neutron and turn it into a proton, an electron, and an antineutrino. So that might be sitting in a nucleus, and that neutron will turn into a proton and send off an electron and an antineutrino. As a diagram, we can think about it looking like this. That's kind of normal, but it's also possible to have double beta decay. Say 2 neutrons turn into 2 protons and give off 2 electrons and 2 antineutrinos. So it's just that same diagram copied and pasted. Why not? Of course, the weak interaction is weak, and so beta decays happen slowly, and so now this requires 2 weak interactions to happen at the same time. So we would never see this because it's just going to be swamped by regular 1 beta decay. Except there are a few very special cases where single beta decay is energetically forbidden, but double beta decay is allowed. One such case is illustrated here for the mass 76 isotonic chain. So I'm showing the energy as a function of number of protons. All of these have 76 particles. And you can kind of understand what we're looking at here, especially from looking at these last 3 terms. There's going to be some quadratic dependence on z. So we're going to get a parabola, and especially centered on roughly equal numbers of protons and neutrons. And then the pairing prefers an even number of protons or an even number of neutrons. And so we're going to get this kind of odd even staggering, that it's more energetically favorable for there to be an even number of protons. So you can see that it's like basically 2 separate parabolas, one for even proton number and one for odd proton number. Or you can think about it going as this zigzag pattern. And it just so happens that now if we look, so if we first say look at gallium 76, you can turn one of those neutrons into a proton, so you increase the proton number and reduce the energy, so you can beta decay to germanium 76. Now, germanium 76, you could turn a proton into a neutron to make arsenic 76, but that increases the energy, and this is actually energetically forbidden. You can't do it. But if you did 2 beta decays, you can go to selenium 76, and that is energetically forbidden. So you won't see a single beta decay from germanium 76, but you can see a simultaneous double beta decay. And so here's a kind of list of isotopes where the nuclear structure kind of is happily coincides to make it so that this is the case, so that there's not a single beta decay, but you can have a double beta decay. And actually, a couple of these are really interesting choices. Among them is germanium, because you can make a detector out of germanium. Germanium's a semiconductor, and so you can make the detector be your material that you're looking at. Similarly, with xenon, you can make a detector out of xenon. And so you can make a very big detector, and you don't need to have like your sample material and your detector in a different place. So this is actually a viable thing to look at. And I should mention that this has been observed in several of these cases, that you can see double beta decay, and it's the slowest decay process that's ever been observed. Now, there's an interesting possibility that connects to neutrinos here, and that is that rather than the regular just two beta decays, you can have neutrinoless double beta decay, where instead of emitting those neutrinos, we have that interaction here, which turns a neutrino into its own antiparticle. And so you can just connect this diagram. So what happens here is you turn two neutrons into two protons and two electrons and no neutrinos. So this would be a distinct signal. And this would be a pretty cool thing, because it would tell you lots of stuff already. Basically, it would tell you the lepton number is violated. It would tell you that neutrinos are Majorana particles. And it would also give you a handle on the neutrino mass through this expression here. So basically, this is the inverse life, or basically the decay rate, the inverse lifetime for this process is given by a product of three terms. One's a phase space factor, so that's just Fermi's golden rule has density of states in there. So there's some phase space, and we know how to calculate that. There's a nuclear matrix element, which accounts for the fact that this happens inside of a nucleus. So there are initial and final many-body states. And then there's what's basically a mass term, which corresponds to this. And so this is just that Majorana mass, which turns a neutrino into an antineutrino. So if we can measure this decay rate, and if we know that nuclear matrix element, this gives us a handle on the absolute mass scale of the neutrino, which is cool. So far, people have been looking for this and haven't seen it, but you can place limits. And so this is not necessarily the most recent limits, but I think it's a nice plot of it. So the way it's often plotted is we don't know what the mass of the lightest neutrino is, and we don't know what this the absolute mass scale is. So this is the combination of mass of basically the mass 1, mass 2, mass 3 that combines into an electron neutrino, goes into here. And so we do know something because we know of the oscillation experiments. So we know something about the masses, and we basically can constrain up to a couple of phases that are not perfectly well known. So there are basically two bands of possibilities, one for the inverted hierarchy that I talked about, and one for the normal hierarchy. And essentially, as you put stronger and stronger limits on the decay rate, you make this m beta beta term, the neutrino mass, have to be smaller and smaller to still be consistent. And so as you do better experiments, this gets pushed down and down and down. Now, the other thing I want to point out here is there's a band on this limit placed by, so here's the Kam-Lanz-End experiment that's using xenon, but other experiments are also increasing and pushing things down. And actually, things are now getting to the point where you're starting to probe this inverted hierarchy band. But this blue band is basically due to the nuclear theory uncertainty on the nuclear matrix element. That's this object here. And it's actually not a proper error bar. It's just given by the spread of some selected nuclear model calculations. And even those are kind of, it's problematic because when you have a model, you want to fit your model parameters to data, but we can't do that because we haven't seen any double beta decay yet. So there's nothing to fit the model to. You have some operator for the double beta decay, and it has a coefficient in front of it, and you don't know what that effective operator should be for your model. So what we really want to do is this with an ab initio calculation, so you can get those parameters from some beyond the standard model theory and start directly ruling out beyond the standard model theories. But to do that, you need to be able to make a connection to these beyond the standard model theories and not have any fudge factors. So I'll talk about more how to do that next week. Okay, so in the final, actually, it looks like I'm doing too well for time. So the last thing that I wanted to talk about is this question of why is there something rather than nothing? So this is the matter antimatter asymmetry of the universe. So there is matter in the universe, and there's more matter than antimatter. And you'd think that naively, in the Big Bang, matter and antimatter get created in equal amounts, and then would recombine and just make photons, and there would be nothing. But there is something, so something must be wrong with that picture. So basically there's this Sakharov presented 3 conditions for baryogenesis. Baryogenesis means, making baryons, or making the baryon asymmetry, which means more baryons than antibaryons, that is more matter than antimatter. And so to do this, you need to have baryon number violation, because if baryon number is conserved, if you start out with 0, you always have net 0 number baryon number. So just baryon number is opposite for particles and antiparticles, and so you should make equal number of particles and antiparticles. And if in order to have some net baryon number of baryons, you have to violate this symmetry. And there are models that can, or I guess kind of schemes that can do this by violating lepton number conservation. And so if you have lepton number conservation, and especially these require this to be done through a Majorana mass, especially usually through a heavy Majorana neutrino, then that lepton number violation can then generate baryon number violation. So neutrinos double beta decay is very interesting for addressing this point 1. But in addition to that, you need to violate C and CP symmetries. So that would be charge conjugation symmetry, and the combination of charge conjugation and parity. These need to be violated. Now we know we have CP violation in the standard model from the weak interaction, but it's not enough to give us the baryon asymmetry that we see in the universe, so there has to be some additional source. And finally, you need to have interactions out of equilibrium. Otherwise, you just have processes happening equally in both directions, and you can't generate anything. So this can happen, for example, during inflation or in the early universe where things are expanding, and so it's not in equilibrium. So I mentioned neutrinoless double beta decay for the lepton number violation, but then we also want to look for some CP violation. And a nice way to do this is through looking for a permanent electric dipole moment. And so why would a permanent electric dipole moment give us that? Well, you can actually, because in the standard model and in kind of generically in a quantum field theory, the combination of CP and T, so that's charge conjugation parity and time reversal, is a good symmetry. If CP is violated, then you need T to be violated. That is, there should be time reversal symmetry being broken. So we can see that. So if we make some sort of a system here that has angular momentum J, and it has a dipole moment, which we'll call D, so the charge is separated. In this case, we have them pointing, let's say, in the same direction, so that the J dot D hat is +1. And now we make a time reversal transformation. So if the angular momentum is from something spinning around, you reverse time, so it starts spinning in the other direction. That reverses the angular momentum. So J goes to minus J. The dipole moment is just sitting there. There's nothing, no time involved. So D goes to D. So the dipole moment stays unchanged. And so now the dot product becomes negative. So we change that dot product under time reversal. It's also it is parity breaking, because you can imagine taking parity means taking x, y, and z to minus x minus y and minus z. It's a spatial inversion. Under parity, J goes to minus J. Oh, sorry, J goes to J. It doesn't change because angular momentum is a pseudo vector. D, dipole moment, goes to minus D because it's a vector, so it points in the opposite direction. So again, that dot product gets a minus sign. So if we were able to observe something that has some spin and a permanent dipole moment, that tells us that nature is not symmetric with respect to time reversal or parity individually. And then in turn, that tells us that CP would be violated too. Okay, so how would you actually go about measuring this? You can do this for examples by putting some sample in a magnetic field and an electric field. And if it's got a magnetic dipole moment, because it's got spin, and it's got an electric dipole moment, then it'll feel a torque of mu cross B. So that's the magnetic dipole moment, and then B cross E, the electric dipole moment. And so this torque will generate a Larmor precession. You can then use lasers to measure the Larmor frequency. And then you can do the experiment with E parallel to B and with E anti-parallel to B. And then that, if there's a dipole moment there, that should change your frequency. And so this is the kind of thing that you can measure with obscene precision. So this is maybe even outdated now, I'm not sure, but in Mercury 199, you put a limit of something like 10 to the minus 29 E centimeters on that dipole moment, and that already starts limiting various proposals or sources of CP violation that should generate this dipole moment. There's a kind of a confounding issue here, and that is that if you're doing this with a nucleus, which is for example, Mercury 199, if this nucleus has a dipole moment, it's then surrounded by the electrons in the atom, and those electrons will have an induced dipole moment and will screen the original dipole moment and cancel it out, so you don't see anything. So that seems to spoil that. Fortunately, that only happens if you have a point nucleus. Nuclei have finite size, and so the screening is actually incomplete. So there is still a signal there, but in order to figure out how that screening actually happens, so what the actual residual dipole moment should be, now you need to go in and do a nuclear structure calculation to calculate what's called a shift moment. So it's something like the dipole moment rate weighted by r squared. And so that's something you need to calculate with theory. And then, so if you have some model of beyond the standard model physics that would generate a permanent dipole moment, then you need to do a nuclear structure calculation to see how that would actually manifest in an atom. And then that's the thing that you can compare with these very precise measurements. So this is the kind of thing now you need to be able to do a nuclear structure calculation with precision and be able to produce an error bar. Okay, so I think I finished faster than I thought I would, but it's usually not too terrible of a sin. So to summarize what I talked about this time around, I just wanted to say that there's a lot of cool physics that we could do. Kind of many of the really interesting questions in physics. We could address these or answer these if we had a way to solve a nuclear many-body problem. And we want to do that not just schematically or with a kind of uncontrolled model. We want to do it in a controlled way, so we have everything, understand all the pieces that are going in there, and then we can produce an error bar so we can actually start making firm statements about this really cool physics. So that's all I wanted to say, and I'll say thank you.
Okay, all right. Thank you for that nice presentation, Ragnar. Now I want to open it to the audience over here. Any questions for Ragnar? Yes, Daniel?
I actually have two, but they are actually stupid, but it's fine. So the first one was on the double neutrino decay, or sorry, the neutrinoless double beta decay.
Yes.
Yes, this diagram specifically. When these two neutrinos, or when one converts somehow to the anti-neutrino, and we get this annihilation, what can they actually annihilate to? Because these are,
It's an exchange.
it's an exchange.
Yeah, so in principle, there should be something that this is some new physics that's coupling to this that generates what you call this, it's a mass. So this is basically at some very high scale, maybe there's some other particle that is existing there. At a lower scale, it's basically just a mass term. So you'd have something in your Lagrangian that has neutrino, antineutrino multiplied by a mass, just like you would for a regular mass term. You'd have, say psi bar psi times a mass, if you've done any quantum field theory. But so that basically, if you think about it, a mass is something that's doing this. If there's just just the particle is there, it doesn't have to interact with anything else. In this picture, it's actually interacting with the Higgs, which is there, but when you write it down as a mass term, it's just the particle moving along. So you can think about this as maybe there's some other particle there generating that mass term.
Okay, yeah,
Think low energy effective theory,
yes.
right down the alley.
And the other one, which seems sort of more playful, is when you're talking about the neutron, when it becomes energetically favorable to go from a proton electron to a neutron neutrino. Just on the sort of thinking on the time scale, as soon as you convert a proton and electron to a neutron, and you have these sort of more nuclear, more neutron filled, the words are tricky. When all of the nuclei are filled with neutrons, does it become easier to squeeze in a sense? Because you've lost the,
Yeah, you basically remove one of these and you start removing them, so then it brings down the Fermi energy again, but then you can squeeze it down. So then the density increases, so then you move the Fermi energy back up. And so there's basically, as you're doing that, you just can shrink it down and you're shooting off neutrinos and turning protons and electrons into neutrons.
okay, so then as soon as you get there, it happens very quickly. That all of these things.
Yeah, I mean, think about it happening basically in equilibrium.
Okay. Okay, yeah, thank you.
Huh?
Okay, any more questions? Experiment people? Hey, in that case, I have one question then. At what energy, at what density roughly can you like stop making any kind of bound states? You said that some energy, some density, you make hyperons and so forth. But presumably at some, if you get to high enough density, you won't even be able to do that, right?
Yeah, so that's the thing. So once you get beyond that, it's anyone's guess, I guess. Maybe you have better guess than I do. At these densities, it could turn into just deconfined quarks or something like this. I think you may remember Larry and Sanjay when we were there had proposed that there's kind of quarkionic matter, which has this kind of like in momentum space, a core of just quark matter, and then towards the high end it becomes hadronic again. So it's just right now speculation, but I guess I think part of the interest is that we have neutron stars out there, and now we're actually getting data from them because now we have gravitational waves and multi-messenger astronomy, so we can actually learn about them. And to the extent that we can then understand all of the stuff, on the outer stuff down into maybe the crust and the core, where we can say we basically know something from nuclear physics, then we can really start constraining what's going on in there, which I think is pretty cool. But right now, yeah, there's a big question mark in there.
Okay, yeah, you give us a foray into sort of three topics that are of interest from that perspective. But I would guess the levels of accuracy that you need for each are somewhat different. So how far do you have to go, and which ones are the lower hanging fruit?
Well, so I can. Well, we'll talk about this a little bit next week, but basically these are all in order of when they've been done. So the stuff about neutron matter has been done a couple of years back now, and double beta decay is just now kind of happening, and the EDMs are work in progress. So, because those are very challenging. So I'll talk about this next week a little bit more, but there is a very nice feature in when you do these calculations ab initio, is that when you go to pure neutron matter, just because of Pauli blocking, a lot of the unknown parameters don't enter, because you say if you have a 3-body force, you can't get 3 neutrons in the same point because you only have spin up and spin down. And so your unknown contact in your 3-body force is unimportant, and so that it removes uncertainty there. So you can actually you can do more precise calculations for neutron matter than you can for symmetric nuclear matter. So this is actually a really good case. In double beta decay, let's see if I get this. So you can't quite read it off of here, but the spread in these nuclear matrix elements from different theories, the nuclear matrix element itself, you can get a factor of 3 different, which then you square it, and so you can get a factor of 10 in the lifetime from that. So I mean, I think they maybe selected just a subset of those for this, but I guess because this is not squared, but so what you'd like, if you could get an error bar that was actually meaningful and was still like a factor of 10, then I think that's an improvement. But what we're seeing is smaller than that. So maybe a factor of 50% or something, something like that is what we're seeing right now, which is already a big improvement. And it's just a matter of believing your error. The EDM, I think, is going to be the most challenging one, because the existing kind of phenomenological calculations, various terms there, they don't even agree on the sign of the terms. And so it can be very difficult to get a good constraint when you don't have the sign of it, right? So that one's going to be challenging, but I think the ab initio calculations are going to be the way to go. If it can be done, it will be with ab initio calculations.
I mean, I'm guessing most of the youngsters here have very little idea of the history of models, right? I mean, the history of this is chock-a-block full with all manner of models, as you mentioned at the beginning, where you don't have any good parameter that would tell you what is going on. I mean, this has a very, very long history with very sophisticated models in place. It's quite interesting mathematical gadgetry out there. can you comment a little bit to give them a little bit of a background of how long a story that actually is? Without
Sure. I mean, so nuclear physics has been going back over 100 years now, and so the models have been going back that far. I think kind of the big workhorses in at least in nuclear structure have been the shell model, which is close to my heart, and I'll talk about that a little bit more next week. Which you can build a lot of intuition out of that, and you can get a lot of kind of good description of spectroscopy at the price of you're doing phenomenology. So you're basically fitting to spectra and then predicting similar spectra. So, and then the other kind of workhorse is mean field theory, or we call it density functional theory, where you can think about things more as like it's kind of a sophisticated liquid drop, and then you can have, rather than being spherical liquid drops, nuclei become deformed, and there's all matter of phenomenology that comes in when things become quadrupole deformed or other shapes. People have, there's lots of kind of being more sophisticated about the pairing that goes in there, making connections to BCS theory and superfluids. So basically, because of this pairing, think of things as superfluids. And so all of those kind of get put in. As there's also then people have historically done a lot of stuff with group theory, with the interacting boson model, which then looks at various kind of representations of groups and trying to classify what's going on. So you can get a lot of kind of understanding about the physics and the relevant degrees of freedom of what's going on. And so there's a lot of value in all of those things, I think. And people have built up lots and lots of lore and knowledge and understanding. The real challenge, though, is when you want to put an error bar on it. I think that's the big snag, is putting an error bar.
So, anybody else? Anything? You're all exhausted. Right, you did a good job. Thank you.
I did it. All right. Thanks a lot.
So let's thank Ragnar again.
See you again next week.
All right, thank you, Ragnar.
We're just turning off recording. If you